All right, everyone, here we are. We're starting a new unit. We're looking at random variables. And random variables are just an extension of probability, whereas probability just kind of says, all right, probability of this event happening is something, or this event not happening, or the joint probability of A and B, that sort of thing. But this is actually going to be sort of different. It's going to look at, well, let's just say maybe a family that has 8 kids. What are the probabilities of having 1 boy or 2 boys or 3 boys all the way up to 8 boys or even no boys, right? So we're going to define a random variable in that case as x is the probability of having 8 boys. And it could be anywhere from 0 to 8, and each one would have an associated probability. So it's a little different. All right, so a random variable is a variable whose value is a numerical outcome of a random phenomena. We use capital letters to denote it. So random variable x is the number of fish I catch in a given night, something of that nature. They follow the rules for probability. We're going to start with discrete. So remember, discrete are countable. Continuous are things that we report on as intervals, more or less. So for example, this is discrete. Toss 4 coins, record the outcome as the number of heads. So it would be countable things like 0 or 1 or 2 or 3 or 4. The number of heads which occur and their associated probabilities. So a discrete random variable x has a countable number of possible outcomes, and we use a probability distribution of x to list the values and their probabilities. So this is what it is. It's just a table, 2 rows, and x could be 1, 2, 3, 4 on up, or 0, 1, 2, 3, 4 on up, or whatever, with the associated probabilities. And maybe this would be 0 for an outcome with a given probability, and this would be 1 for an outcome with maybe the same probability, maybe a different one. Just depends. So anytime you see something like this with a little subscript I like that, it just means the individual probabilities. So in a discrete random variable, each individual probability must satisfy 2 requirements. The first being that each individual probability is a number between 0 and 1. Yeah, okay. We get that. Probabilities are between 0 and 1. And if we get a complete probability distribution, the sum of all of those individual p sub i's or individual probabilities should also equal 1. All right, you find the probability of any event by adding up the probabilities, individual ones, p sub I, of the particular values of individual x's, or x sub I, that make up the event. That's a lot of stuff. It really doesn't make too much sense. But let's just go back to that flipping 4 coins problem. And let's just say I want to know the probability that x is less than 2. Well, that would be either 1 head or 0 heads. And so we would get the 2 and add them up, because or means add, or greater than 2. That would be 3 or 4. Those probabilities would add up too. So that's how we get the probability of any event, depending on how that event is described. So here's the 4 heads. That's 16 outcomes, remember, 2 to the 4th power. So there's one way to get no heads, one way to get 4 heads. These are out of 16. There are 4 ways to get 3 heads and 4 ways to get 1 head. They're all listed. So that's 4 out of 16, or 1/4, 0.25. That's the same thing. And then we have 6 out of 16, and we can report them as fractions or decimals, but let's look at a probability distribution. So there it is. All right, these are reported as decimals, but you can see 1/4, 1/4. This is the decimal equivalent for 6 out of 16, 1 out of 16, 1 out of 16. Each one of them is between 0 and 1, and all of them should add up to 1. All right, we can also represent this as a probability histogram, and we can do it on the calculator. Now, I'm not going to do this example. I will show you an example on the calculator here in a little bit, but it won't be this one. And once we have this histogram, we can describe that distribution. So here is the distribution for this one. All right, it is unimodal, so it's single peaked, and it's symmetric. I would probably not go so far as to call it bell shape or normal. It does give you that impression, but we've got some problems here, not the least of which is that we're looking at an area model for something that's really doesn't lend itself to area. So like 0 is just one value. It's not like -1/2 to 1/2, right? They're just doing that to create an area model. But like for 1, all the probability is at 1. So if I want to know the probability of 1.5, that would be, well, let's go back to the table. All right, 1.5 would be here. There's no number there, all right? So the probability that x equals 1.5 here is 0. But the probability that x is less than 1.5 would be either a 1 or a 0, and you'd add those two up. See the difference? So if I have 2 2/3, that would be, the probability of that would be 0, because we actually don't have a number of heads that would be 2 2/3. Okay, so getting back to the histogram, the area model is a little bit of a stretch, so let's just call it symmetric and single peaked, or unimodal is a good way to put it. Yeah, so it's good for symmetry and that kind of thing, but an area model is a little bit of a stretch. All right, so the event of tossing 4 coins and getting 2 heads, write this in terms of x. Okay, x equals 2. What's the probability that x equals 2? All right, remember from the table, that was 0.375. That was our biggest probability in the middle. The event of tossing 4 coins and getting at least 2 heads. All right, at least 2 heads means 2 or more, so that would be 2 or 3 or 4. All right, so that's the probability that x is greater than or equal to 2, which is also equivalent to the probability that x is greater than 1. You could say it that way when things are discrete. But there's the probability of 2 or 3 or 4, and that adds up to that. Greater than 2, that would be 3 or 4. Right? There's the probability that x is equal to 3, probability that x is equal to 4, that's or. So they add up to this. All right, the event of obtaining at most 1 head when 4 coins are tossed, at most means that much or fewer. Like if I have at most $20 in my pocket, I have 20 or less, right? So that would be the probability of x is what? Less than 2, or x is less than or equal to 1. So that would be 1 or 0. Probability of x equaling 1, or the probability of x equaling 0. So you add them up. All right, we have a worksheet that you will do for homework, but we also have a note sheet on page 1. So I want to go ahead and get out of here and set up for that. And so you know how that's pretty instantaneous, so hold on. All right, so here we are, we're back, and this is page 1, and we have this Apgar scale for baby's health. The higher the number, the healthier the baby is. And it's a rating based on skin color, heart rate, muscle tone, breathing, and response, like getting your feet, the bottom of your feet tickled or something like that. And those are all recorded and put on a scale from 1 to 10. And this is a pretty old scale. It even predates me by like 5 years. So this has been around for a long time. And since you can go anywhere from x equals 1 up to 10, all right, and this has been going on for so long that babies have been rated and recorded and rated and recorded thousands upon thousands of times. So we now have a working probability model, probability distribution for this random variable. And we're supposed to show that the probability distribution for this is legitimate, okay? So let's go ahead and just say that there were the two things we were supposed to check. So let's just say all probabilities listed up here are between 0 and 1. All right, that's the first thing. And I'm going to just kind of ask you to trust me on this. All probabilities here do add up to 1. I did check that. So all probabilities add up to 1. Okay. So it is a legit probability distribution for this particular random variable x, which is Apgar scores. All right. So the next thing on the agenda is to produce this guy, this probability histogram. And this number 2 up here does have instructions on how to do it on the calculator, but so do I. So here it is. What you want to do is go home and open up one of these things. We don't actually need that. So let's go back here. And this is just, this column here represents the top row. Label it X. Please put a label on it. It's got to be X. That was 0 to 10, right? And all those numbers should look familiar. Put in the probabilities, so label that PROB and put them all in. And why don't you hit pause and do that? Okay, so now that this is in, we need to go ahead and open up a graph page. All right, just ignore this page here. We don't really need it. And what we want to do is click down here, and this will be the variable x. And everything settles down like you would expect. Now, this is going to be the tricky part. I know that you want to add this variable probability here. That's not going to work, right? What you want to do is go to Menu and Plot Properties, and we want this number 9, Add Y Summary List, and we want to add probability as that summary list. And there it is. Nice, beautiful histogram. It does a great job. The NSpire does. And looking at this thing, if I had to describe it, I would say, yep, this thing is skewed to the left. Just like this guy is skewed to the left. So let's just say, describing the distribution, we can just go ahead and say that the distribution, or the histogram, is skewed to the left. Can't really point out anything else. We will, in a day or so, figure out how to calculate the mean of this thing, which will be like the balance point, and even the standard deviation. So that's good stuff. All right, so finally, number 3, doctors decide that the Apgar scale of 7 or higher indicates a healthy baby. Well, looking up here, that's a pretty good thing, because if you note 7 or higher, a good chunk, if not most of your probability is located up there. They're just little tiny probabilities below that for the most part. All right, so let's see what they're going to ask us. It says, what is the probability that a randomly selected baby boy is healthy? All right, that's 7 or higher. All right, so that's the probability of, let's see if we can get that up here. 7 is 0.099, so this would be the probability that x is greater than or equal to 7. All right, or you could say probability that x is greater than 6. That'll be 0.099, and I conveniently left my cheat sheet away, so plus 0.319. plus 0.437 plus, and this last one I remember was kind of small, 0.053. And if I remember correctly, that adds up to 0.908, which is good. Like, that's saying like roughly 91% of babies show up as healthy. That's kind of what we want. We'd be nice to have it higher, but well, we'll take it. So what's the probability that a randomly selected baby isn't healthy? Well, that's the complement of being healthy. So we can say this is the probability that X is less than 7, less than or equal to 6, and that's just 1 minus the probability that X is greater than or equal to 7, right? So that's 1 minus 0.908, which is 0.092. All right, so yeah, about a little over 9% of the babies aren't healthy, but again, that means 90% are. That's a good thing. All right, the probability that the baby scoring greater than 7, and that's just going to be everything but that right there. So that'll be 0.319 plus 0.437 plus 0.053. And hold on just a moment, because I don't happen to have that handy and I don't remember what it is. So let me pull out my trusty calculator here. So 0.319 plus 0.437 plus 0.053. And I'm getting, that can't be right. Hold on. 0.908 minus 0.099. 0.809. Sorry about that. Okay, so this is what we are covering, and if you flip the page over, you'll see the worksheet, and that's what's going to be due tomorrow. So knock it out, and we will continue with this when we meet again.